So we had mentioned previously that to find extrema for functions of one variable, we would do the following. So the first thing is we find the critical points of the function. Then we classify those critical points. And then once we have those critical points, we plug them into the function and we compare the values of those critical points to the values of the function on the boundary. And this is the thing that we're going to focus on today, having done the previous two on the last day. So suppose that the function is defined on the interval AB. Let me draw this out for us here. On this interval here, this is where we use the critical points, right? So for everything that's inside. And these are the boundary points right here. And that's fine. This is how we would attack the problem of finding maxes and mins. We find the critical points on the inside, compute f of those points, and then f of the boundary and compare them. So when we have a function of multiple variables, we might be faced with a question like the following. So let's say that we're asked to find the max and min of a function of two variables on the set x squared plus y squared is less than or equal to 1. Okay, so this is the disk. So you take the unit circle and you fill in everything inside. And on the inside, we know that we can use the critical points to find maxes and mins. That's what we did last time. But the question is, what do we do now for these boundary points? There's infinitely many of them, so we can't just plug every single one of them in individually. We're going to need something a little bit stronger than that. This leads us to the following theorem. So suppose that I give you two differentiable functions on Rn, and I take the set of points where g is equal to 0. So this is a weird set, and you might be confused as to why we're defining this thing this way. I'll come back and I'll talk about this a little bit later. So if f achieves a max or a min on S at the point C, then there exists some real number lambda such that the gradient of f at C is lambda times the gradient of g. Okay, so if we look at what this is actually a system of n nonlinear equations in n plus 1 unknowns, because the lambda there is also an unknown. But if we add to that this g of x being equal to 0, that gives us n plus 1 equations and n plus 1 unknowns. And that's exactly what we need to be able to, find all of the variables. So the idea of what this set S means, where g of x is equal to 0, is that we want to be able to write the constraint set as an equation. If we think about, the example that we had just done, the one on the unit disk, our constraint set was the circle, right? X squared plus y squared equals 1. And if we rewrite this, then this thing right here is our g of xy. Okay, so g of xy is how we write the constraint set. Now, it's worth noting that some people sometimes talk about Lagrange multipliers in a slightly different way. So they define the Lagrangian function, this stylish L, and it's f minus z times g of x. And this is a function of n plus 1 variables, right? We have the x variables the n variables from x and the 1 variable from z. And the theorem now goes that if f achieves a max or a min at a point C, there exists a lambda in the real numbers such that C lambda is a critical point of L, right? Namely that the gradient of L at that point is equal to 0. And this defines the exact same set of equations as we had above, where the gradient of f was lambda times the gradient of g, but it also includes inside of it this fact that g of c has to be equal to 0. So let's run an example. So let's say that you're asked to find the max and min of the function xy, and we're going to do this on the set, this ellipse here. So in order to do that, first thing we should do is we should write down what the constraint function is. And let me draw this thing for you. It's going to end up being an ellipse whose semi-major axis has radius 3, and semi-minor axis has radius 2. And we're trying to find the max and min on the orange set. Okay, so let's compute the gradients of these things. And again, they're all just polynomials, so it's not too much work. And now if we employ the theory of Lagrange multipliers, we know that there exists some real number lambda such that the gradients are proportional to one another through lambda. Now I like to write these equations down vertically. This is going to give us a system of equations. If I write them vertically, I think it's just easier to kind of see the manipulations that I'm supposed to do. So setting gradient of f equal to lambda gradient g, this is what we get. And now we need to solve this system for x and y, potentially lambda as well. So what I'm going to do is I'm going to sub-equation the second equation here into the first one. And if I do that, plug that in here, and you can work that out, that's 144 lambda squared y. Now I'm going to put everything on the same side, right? So I'm going to make this equal to 0. And I'm going to factor out a y. And we know that when you have the product of two things being equal to 0, one of those two things has to be equal to 0. So that tells us that either y is 0 or this 1 minus 144 lambda squared term is 0. So we got to break this into cases. In the first case, we're going to set y to be equal to 0. And if I use the second equation, then I know that x is equal to 18 lambda y, which is equal to 0 because y was 0. So x has to be 0 as well, and I get the point 0, 0. If I go back up to my diagram and I fill this in here, notice that this isn't in the red space. Right? So this can't be possible. Now, if we want to write this down more algebraically to see it's algebraically impossible, we are going to substitute this back into the constraint. So 36 is 4x squared plus 9y squared. And if we plug those in, we get 36 is equal to 0, which is obviously not possible. Having dealt with y equals 0, let's go to the second case. So let's suppose that 1 minus 144 lambda squared is equal to 0. We can rearrange this thing so that lambda squared is 1 over 144, so lambda is plus or minus 1/12. So lambda can be either plus 12 or minus 12, so we have two more cases. So let's suppose that lambda is 12 to begin with, and let's plug this into the first equation, y is equal to 8 lambda x. So if we plug lambda equals 1/12 into that, we're going to get that y is 2/3 x. And now I'm going to take that and I'm going to sub that back into the constraint function. And if I do that, right, we're going to plug in 2/3 x here and square it all. I get 4x squared plus 4x squared, which simplifies to 8x squared. And that allows me to actually solve for x squared. Oh, sorry, this should be 36 over 8. Great. And so I get plus or minus root 3 over 2. Now to figure out what y is, remember that we knew that y was 2/3 x. So I'm just going to plug these back in, and that tells me that I get this set of possible functions. They both have the same sign. And these are potential candidates for maxima and minima. So we'll come back and we'll look at those again in a second. Let's now look at the second possible case and see if we can get more potential candidates. So lambda equals, sorry, that should be negative a 12th. And this time, if we look at the previous example, if I plug lambda equals negative 1/12 into 8 lambda x, it's the exact same working, so I'm going to get y is equal to negative 2/3 x. And then looking even further down, if we look at what's going to happen when I plug this into the constraint function, if you look here, you can see I'm going to get 2/3 or negative 2/3 x squared, and that minus sign is just going to disappear. So I'm going to get exactly the same answer. I'm going to get 36 is equal to 8x squared. And so we can conclude that x is the same possible collection of points plus or minus root 3 over 2. But this time I have to use the fact that y is equal to negative 2/3 x. So when I plug x back into this in order to solve for the y, I'm going to get the y is, the same set of points in magnitude. It's going to be 2 divided by root 2, but it'll have the opposite sign of whatever x has, right? So if x is positive root 3 over 2, y is going to be negative 2 over root 2. If we put all of this together, this means now that we have 4 candidate points. So the first coordinate is root 3 over 2. The second one is root 2 over 2, and the 4 points come from the fact that we have to choose the signs for each of these points. Now, what we want to do is we want to determine the global max and min, so we're going to plug these back into the function f. Now, f is just the function x times y. So if x and y have the same sign, they're going to give me the same value. So if I plug in the case when they're both positive, or if I plug in the case where they're both negative, I'm going to get the same answer. And we'll multiply this out, and we'll get root 6 over 4. Now, on the other side of things, when the signs are different, we're going to get exactly the same number out, root 6 over 4, but we're going to pull out that minus sign. So let's write that in, this time with the signs being different. And like I said, same answers before, but with the minus sign. This guy is the maxima, these guys are the minima, and there we have it, we've solved the problem. So this time now, let's do a slightly more complicated example. Let's say that we have to worry about the interior of a set as well. So let's say that we want to find the extrema of the function x squared y. And we're again going to do that on the interior of an ellipse this time. X squared plus 2y squared is less than or equal to 6. Let's start by actually drawing this thing. Again, we're going to get an ellipse with semi-major axis root 6 and semi-minor axis root 3. And this time we're actually trying to solve this on the interior of the set as well. So we're going to have to use our critical point technique. So let's focus on the interior first. Computing the gradient of f, it's again just a polynomial, so it doesn't involve too much work. And we're going to set this to 0, 0. And this gives me two systems of equations. Now the second equation forces x to be 0. And if I plug x equals 0 into the first equation, it's automatically satisfied. So that tells me that y can be absolutely anything. Now look back at the figure here. That gives me the entire y-axis between negative root 3 and root 3. That whole thing is a critical set. So we can write that algebraically like this. And let's try to classify these critical points by computing the Hessian. So we compute it in general first. We'll get 2y, 2x, 2x, 0. And now if I plug in x equals 0 into this, we get a big matrix of zeros, mostly zeros. And if I compute the determinant, well, the determinant unfortunately is 0 as well, so the second derivative test is actually inconclusive. Now, on the other hand, it's relatively easy to argue that, or to see that if I plug 0y into the function, I just get the number 0 out. And this cannot possibly be a maximum or a minimum, because it's easy to make the function greater than 0 or to make it less than 0 just by choosing any points x and y near the y-axis. So we can pretty much eliminate this as being an extreme value. If we choose now to focus on the boundary points, so again, we're going to write the constraint down as a function. And we're going to take its gradient, so 2x for y. Then again, if we choose to invoke the theory of Lagrange multipliers, we know that there's going to be a lambda such that the gradient of f is equal to lambda times the gradient of g. And I'm going to write this system of equations down vertically. For convenience, let's just number these equations. And I want to focus on equation 1 to begin with. So I'm going to push everything onto one side, set this equal to 0. The 2's are definitely going to cancel out, and I'm going to factor an x out of everything. Once again, here we have this situation where the product of two things is 0. So one of the two things has to be 0. So either x is 0 or y is equal to lambda. So we've got a couple of cases here. Case 1, let's take x to be 0. So now looking at equation 2, if I plug x equals 0 into this, I get 0 is equal to 4 lambda y. Again, product of two things being 0, either y is 0 or lambda is 0. So we have subcases. Let's suppose that y is 0. Well, we've now said x is 0 and y is 0, and that's impossible, because if we plug this into the constraint, we get 6 is 0. Obviously nonsense. The second case, let's suppose that lambda is 0. And in this case, both of our equations are actually satisfied. Right? If we go back and we look at what the original function was, if I plug x equals 0 into the top equation, I get 0 equals 0. X equals 0 in the second equation tells me 0 is 4 lambda y, but if lambda is 0, I again get 0, 0. 0 equals 0. So y can be absolutely anything. And if I take that and plug that into the constraint equation, I can solve for y and get plus or minus root 3. So I get two candidate points, 0, plus minus root 3. And that takes care of the x equals 0 case. So let's do case 2 now. Let's suppose that y is equal to lambda. And I'm going to sub this into equation 2. So that will give me x squared is equal to 4y squared. And if I plug this into the constraint equation g, everything is now in terms of just y squared, and so I can solve to get y is plus or minus 1. Using the fact that x squared is equal to 4y squared, which is just 4, I can now solve for x to get plus or minus 2. So this gives us 4 candidate points, right, depending on the signs of the 2 and the 1. So we're going to check whether they're maxes or mins by plugging them back into f. Remember that the function f is x squared y. So when I plug in 0 plus minus root 3, I get 0. That's not a max or a min by exactly the same reasoning of what we did for the interior point. Now, on the other hand, what we realize is that the sign of x doesn't matter. So when I plug in plus or minus 2, plus or minus 1, the sign of x doesn't matter at all. So the sign of y is the only thing that's going to make a difference. So let's do the positive y, I get 4. When I do the negative y, I get negative 4. And so this thing is a max, this thing is a min, and I'm done. All right, so now you're in a position where you should be able to solve most of the optimization problems that you're given. You first work on the interior, you then work on the boundary, and once you have all of your candidate points, you plug them into your function f and you figure out which is the biggest and which is the smallest, and that will take care of it for you.